Hi, I have created this power performance and thermal simulator that I'd like you guys to try it out. My motivation behind doing this is to sort of understand how the PPT equations interact with each other, because these equations are highly coupled, nonlinear and dynamic. So we obviously cannot have like an analytical equation to understand how the convergence or optimization of PPT actually works. So we have to take more like a simulation based or numerical approach, which is what I have tried out here. So in this video, I'd like to go over the modeling aspects of power performance and the thermal, and describe how it's used in the simulator. So let's first look at the power model. As we know, power consumption of a processor is equal to its dynamic and the leakage power. So let's first look at how dynamic power is implemented or is modeled in this simulator. We know that P dynamic is equal to C V square F. C here is the effective capacitance of the switching transistors in the processor, and V is the VDD, and F is the clock frequency. Now we know that V and F is going to be controlled by the DVFS algorithm, and here I'm introducing a new term called switching activity. Now the way I have defined switching activity is like this. So this alpha of F of W is equal to 0.5 plus 0.5 times W, and this new term W is basically workload mix, and this is a number between and 0, 1. So what this workload mix means is that if this W is, let's say, 0, then that means the CPU is somewhat in a semi-idling state, and it's fully memory bound, and it's trying to fetch data from the memory. And if it's set to 1, then it is in full compute mode, and the transistors in the processor are switching. So basically, if we set W to be 0, we will get alpha of W to be 0.5. If we set it to 1, we will get it to be 1. So basically, for 0.5, it means it's memory, and if it is 1, it is compute. Now, if we substitute that back in here, what it means is, let's say we set W close to 0, then it means that we are somewhat reducing C effective, meaning the number of transistors that are switching are significantly less. So the way this is implemented in the simulator is that this is a sliding scale, and it's a number between 0 and 1. If it is close to 0, then that means it's more memory intensive. If it's close to 1, it's more compute intensive, and we will when it's close to 1, obviously we will have much more dynamic power than when it's close to 0. So that's the idea of the switching activity. So that's basically the dynamic power. Okay, now let's look at leakage power. Leakage power is defined like this, this equation here, and P leak is equal to P leak 0 times an exponential term that's sensitive to voltage and another exponential term that's sensitive to temperature. Now this P leak 0 is treated like a modeling constant, and I've set that value to 0.6 watts at 25 degrees C. And also, let's say we can also think of it as at voltage equal to 0.8 volts. 0.8 volts. And the idea behind choosing this value of 0.6 watts is that it gives us a realistic looking battery drain behavior in the simulation. That's the reason why this is chosen. And also the way these exponentials are defined, let's say if V is equal to 0.8 volts, then this will become e to the power 1. It will be, this entire term will become 1, and if t is equal to 25, it becomes it goes away. So basically we will have a leakage power of 0.6 watts. Now further, in the DVFS table we have set the lowest voltage that it can go to is 0.8 volts basically. Now the idea of these exponentials is that and the constants, the A and B constants here are like the sensitivity parameters for the voltage and temperature. So for voltage, this value A is set to 2. So now what this means is that for, let's say, for 1.8 volt increase in voltage, this term will become like E squared, which is approximately comes out to be 7. So for every 1.8 volt increase in voltage, we will see like a 7 times increase in the leakage power. And similarly, for the temperature, let's say if T is 50 volts, 50 degrees C, then this term will become e to the power 0.04 times 25, which is equal to e power 1 approximately. That will come out to be 2.7. So basically what this means is for every 25 degree increase in temperature, we will see a 2.7 times the increase in leakage. The other thing to highlight is that leakage power is much more sensitive to voltage than it is to temperature. That's why these constants were chosen with that in mind. And leakage power obviously is very important. If we're running a load for a very long time, then leakage power will climb up to be much higher than the dynamic power. Hence these numbers and the modeling of the leakage power is done like this. So with both dynamic and the leakage, we can finally calculate the total power. So that's the idea behind doing the modeling for the total power. And now let's look at how we can model the temperature rise in the system. So now the steady state temperature rise for a constant power is given by this equation, and which is equal to the ambient temperature plus the product of the total power, which we just calculated, times the thermal resistance. Now, what is steady state temperature? So steady state temperature is the temperature that the system will stabilize to when there is generation and dissipation of heat. When there is a certain amount of generation and dissipation of the heat, depending on the thermal resistance of the system, whatever temperature that we attain is the steady state temperature. And when we start running the processor, the temperature of the processor wants to get to the steady state. That's the basic idea here. And the other thing is this steady state temperature can be higher than the skin temperature. So when the temperature climbs up to anywhere close to the skin temperature, then DVSS will cap the voltage and frequency such that we start reducing in temperature. Now the way the temperature rises in the system is modeled by this first order RC model. So let's see how that is done. I've written a much more. So this equation looks a little bit too many terms, too many parentheses. Basically, I have more simplified equation here. So what this is saying is the new temperature is equal to old temperature plus the steady state temperature minus the old temperature times the first order RC term. Okay, 1 minus e to the power minus t by RC, and this RC is basically the thermal time constant. Okay, so basically we will use the temperature of the system plus the max, which is the steady state temperature, and we take out the subtract the old temperature, and we multiply it with e to the power minus t by RC. So if the this thermal time constant, if this is a very large number, meaning very high heat capacity in the system, the rise and the fall of the temperature in the system will be very slow. If this is small, it will be much faster. So to illustrate the idea a little bit more clearly, I have this plot. So basically, let's say tau is set to 30 seconds, then we will see the rise and fall like the blue curve here. And if it is set to 200 seconds, then the rise and fall is going to be much slower. And the other thing to highlight here is that if we have a very idealized curve for the steady state, which is the red plot here, then the rise in the temperature, rise or fall in the temperature in the system will follow like this RC, that it's every time it's trying to catch up to the steady state, and obviously this is going to be capped by DVFS if the steady state temperature goes above the skin temperature. So that's the idea of modeling the temperature. So now let's look at how we can model the performance. This is pretty straightforward. Obviously, this is a very simplified model. So performance is equal to IPC of W, IPC's instructions per cycle, and this is dependent on the workload that we defined earlier times the frequency of the operation. So that gives us the performance. In reality, since this performance is expressed in million instructions per second, we will have to multiply this by a factor of 1,000 because this is in gigahertz. Now, the way the IPC is going to be modeled is following this equation here. The idea here is that we model how the workload shifts between memory and compute. Now, we set two constants here. One is IPC min and IPC max. So IPC min means IPC min has a value of 0.5, which we get if W is equal to 0, which we defined earlier. This means that we are executing one instruction in 2 clock cycles. And IPC of max is set to a value of 2. This indicates, or this is more for the compute case. This means it's executing 2 instructions in 1 clock cycle. So this way we shift the workload between memory and compute with this workload mix, and that goes into here, and we will calculate the performance, which is just a simple arithmetic calculation. Okay. Now, along with power performance and thermal, I also thought I should include energy. The idea behind including energy was to show how the battery drains. I mean, we don't have infinite battery, so I thought it would be cool to include the battery power and how it depletes. Energy is simply basically power times time, P times T, and this is expressed in joules. So if we want to convert this to watt hour, then we just divide it by 3600 seconds, and we get this in watt hour. So the idea is it's the energy curve is basically cumulative, meaning it never goes down. So we just continuously add energy to to show that it keeps increasing, and as this goes up, the battery percentage goes down following this equation. Basically, the battery watt hour minus the energy watt hour divided by the battery times 100 gives the battery percentage. So that's the idea in modeling energy. So if we go back and look at the GUI of the simulator, these are the parameters that we have. We have the workload mix that explain this is between 1 and 0, and we can slide and select the value for the workload mix. And then I've also given C effective, which we can set. In this simulation, I'm running that at 1.2 nanofarad, but the user can change this. I've also included the option to manually override the frequency and voltage. If it is left unchecked, then the DVFS table here will take over. If we select this, then we can actually see the impact of the voltage and the frequency individually. And also, user can select the ambient temperature and the thermal limit, the skin temperature set it to 42 degrees C here. And then I've also defined something called overheat grace. What this means is if the voltage hits the thermal limit, then if we don't have this overheat grace, what happens is the DVFS starts to oscillate. So if we give it some time, let's say like 5 seconds here, then we can have a much graceful movement in the DVFS algorithm. In fact, one of the toughest things to do was to avoid the oscillations in the DVFS table, for which I had to include something called DVFS hysteresis compensation, so that it doesn't oscillate too much. It's probably not real. In reality, probably people use like a machine learning algorithm to control the DVFS. And the user can also set the battery capacity. Here I'm using 1 watt hour to show that, okay, if the workload is too high, and they can also set the thermal constant here, is too low or too high for that matter, how the battery gets drained. And then the total workload is set to 10,000 billion instructions, so that basically 10 trillion instructions with this much battery, and we can see how the performance will change based on the rise in temperature. And then the thermal constant, which we just talked about. This is a value that depending on the thermals in the system, the user can set this. Obviously, as described, if this is set too low, we will see much faster rise and fall in temperature. So it's set high, it's much slower. So this needs to be set somewhat judiciously. So when we hit play, it will start cranking the numbers, and you will see the changes in the plots dynamically. And you can also speed up the simulation and by 20x, 100x if you want to see quickly how the whole thing works. And also the performance, the thing that we just described, is shown here, and it also shows the time elapsed and the amount of workload that is remaining. Okay, so that's pretty much how this simulator works. So please give it a shot and let me know if there's any thing worth discussing, anything that interests you. All right. Thanks a lot. Take it easy. Bye.